Dear students, having discussed the nature of distributed log models, now we consider the estimation of distributed log models. We consider two types of distributed log models. One is the finite distributed log models, where the log length is specified. For example, if we specify yt as equal to alpha plus beta 0 xt plus beta 1 xt minus 1 plus etc. beta k x t minus k plus ut. This is an example of a finite distributed log model. The reason is log length is specified. The second is infinite distributed log model, where yt is equal to alpha plus beta 0 xt plus beta 1 xt minus 1 plus etc. plus ut. This is an example of an infinite distributed log model. This is infinite because the log length is not specified. Now the question is how to estimate alpha and betas. There are two approaches to the estimation of distributed log models. One is the ad hoc estimation. Given a distributed log model, we simply estimate the parameters by taking xt, xt minus 1, etc., xt minus k as the lags of distributed, as the lags. That is ad hoc. The second is we estimate the distributed log model by imposing some restrictions on the distributed log coefficients betas. We estimate the parameters of the distributed log model by imposing some restrictions on the parameters betas or the distributed log coefficients betas. We will not explain ad hoc estimation because ad hoc estimation is not extensively used in econometrics because it has no theoretical basis. So what we consider is only the second, estimation of a distributed log model by imposing restrictions on the behavior of betas, the distributed log coefficients. We first consider the Koyck approach to distributed log models. Koyck approach is very famous in econometrics as a method of estimating the coefficients of distributed log model. So we first explain the Koyck approach to distributed log models. Koyck approach. In the Koyck, to explain the Koyck approach to distributed log models, we assume that we have an infinite distributed log model. We assume that we have an infinite distributed log model where yt depends on xt, xt minus 1, xt minus 2, etc. etc. Now, assuming that betas are all of the same sign, that is, betas will not change the signs, Koyck assumed that betas decline geometrically, assuming that all the betas having same sign. Koyck assumes that betas decline geometrically by the relation beta k is equal to beta 0 lambda raised to k. Beta k is equal to beta 0 lambda raised to k, where k is equal to 0, 1, 2, etc. The lag structure specified by Koyck is beta k is equal to beta 0 lambda raised to k, where k is equal to 0, 1, 2, etc. up to infinity. If k is 0, you have beta k as equal to beta 0. If k is equal to 1, beta 1 is equal to beta 0 lambda. If k is equal to 2, beta 2 is equal to beta 0 lambda square, etc., etc. Beta k is equal to 0, beta 0, k is equal to 1, beta 0 lambda, k is equal to 2, beta 0 lambda square, then beta 0 lambda cube, etc., etc. Lambda is such that lambda lie between 0 and 1. Lambda lie between 0 and 1. It is such that it is known as the rate of decline or decay of distributed lag. Lambda is known as rate of decay of distributed lag, and 1 minus r lambda is known as speed of adjustment. 1 minus lambda is known as speed of adjustment. Lambda is known as the rate of decay or the rate of decline of the distributed lag. 1 minus lambda is known as the speed of adjustment. What it says is, if the value of lambda is very high, speed of adjustment is slow. If the value of lambda is low, value of lambda means 1 minus lambda is very high, speed of adjustment is quick. That we will explain with the help of an example. So lambda is the rate of decay, 1 minus lambda is the speed of adjustment. Now, what this mechanism says is, the value as lambda is assumed to be between 0 and 1, the value of successive betas is numerically smaller than the preceding betas. That is, beta 0 is greater than beta 1 because it is a fraction, beta 0 into fraction. So beta 0 is greater than beta 1, greater than beta 2, like that. And this is a reasonable assumption because as we move towards the back, the impact of distant past on present value of the variable will be lower than the impact of recent past. That is, recent past has more influence on present than remote past. So, it is a very logical assumption. It is a very logical assumption because it is a nature of economic relationships. And as I told you, if the value of lambda is very high, speed of adjustment is low. If the value of lambda is small, speed of adjustment is very quick. As an example to this, consider this graph. Suppose this is beta k and it starts with the beta 0. Beta 0, it is lag. Now, as we 1, 2, 3, 4, etc. If the value of lambda is small, beta k approaches to 0 very quickly. So 1 by 4 is equal to lambda. If the value of lambda is say 1 by 2, it approaches to 0 slowly. If the value of lambda is say 3 by 4, it approaches to, that is the rate of decay, the speed with which betas decreases to 0 decreases as the value of lambda increases. So lambda is the rate of decay, 1 minus lambda is speed of adjustment. Lambda very high means 1 minus lambda is small, speed of adjustment is quick, and vice versa. Let us see this with an example. See this with an example. Now, suppose that we specify two values for lambda. Lambda is 0.75, lambda is 0.25. Initially beta 0, so beta 0, beta 0. Now, what is beta 1? Beta 0, that is 0.75 of beta 0. Beta 2 is 0.56 of beta 0, and beta 10 is 0.06 beta 0. That is, even after 10 periods, beta 10 is not equal to 0 because lambda is very high. Then is 0.25 means 0.25 beta 0, then it is 0.06 beta 0, and it is almost 0. That is, if the value of lambda is small, then the adjustment to 0 is very quick. That is, betas approaches to 0 very quick, in addition to beta 0. In both cases, beta 0 is same, but beta 1, beta 2, etc. approaches to 0 quickly if lambda is very high than lambda is small. So lambda is the speed of adjustments. 1 minus lambda in the first case is 0.25, small value, adjustment is low. 1 minus lambda in the second case is 0.75, very high, adjustment is quick. So if 1 minus lambda is small, adjustment is slow. If 1 minus lambda is large, adjustment is quick. And 1 minus lambda is known as speed of adjustment. And the mechanism suggested by Koyck is beta k is equal to beta 0 lambda raised to k. This mechanism is known as geometric decay, the mechanism suggested by Koyck. Now this is the Koyck model, and this is the Koyck model. Now let us see what are the features of this Koyck model. Now the first feature is, assuming that lambda is between 0 and 1, non-negative, Koyck rules out possibility of betas changing signs. If betas are positive, then beta 0, beta 1, beta 2, etc. are also positive, because lambda is between 0 and 1. So betas will not change signs. For example, if Y is consumption, X is income, this is the impact multiplier, that is the increase, the MBC corresponding to the same period, then beta 1, beta 2, etc. all the successive values will be positive. So betas, even though they are numerically smaller, the sign will not change. The second one is, feature of Koyck scheme is, assuming that lambda is less than 1, Koyck gives less weight to successive betas. Successive betas or distant betas than current betas. This is economically plausible because recent past has more influence on present rather than remote past. The third feature is, he assumes that the sum of betas which give the longer run multiplier is finite. the sum of, as we have discussed earlier, beta 0 is impact multiplier, beta 1, beta 2, etc. are known as interim multipliers, beta 0 plus beta 1 plus etc. known as long run multiplier. In our case, sigma beta k is equal to 0 to infinity is equal to beta 0 plus beta 1 plus beta 2 plus etc. This is equal to beta 0 plus, what is beta 1? Beta 0 lambda plus beta 0 lambda square plus etc. Beta 0 plus, since beta 1 is beta 0 lambda square etc. And you can see that this is an infinite geometric progression with the first term beta 0, common ratio lambda. So this can be, and as the sum of a geometric progression is written as, for example, a plus a r plus a r square plus can be written as a into 1 minus r raised to n by 1 minus r. If r is less than 1, r raised to n approaches to 0 as n approaches to infinity, then it becomes a by 1 minus r. So using this we can write it as beta 0 into 1 by 1 minus lambda, or equal to beta 0 by 1 minus lambda. So if we know the value of beta 0 and lambda, we can calculate the long run multiplier. We can calculate the long run multiplier if we know the value of beta 0 and lambda. And in all the situations which we will discuss, the value of beta 0 will be known, and the value of lambda will also be known, so that we can calculate the long run multiplier, which is given as beta 0 by 1 minus lambda. Also, using this property, we rewrite the Koyck model as yt is equal to alpha plus beta 0 xt plus beta 0 lambda xt minus 1 plus beta 0 lambda square xt minus 2 plus etc. ut. Using this, we rewrite the model as, instead of beta 1 beta 0 lambda, beta 2 beta 0 lambda square etc. So this is our model. Now this is the original model we have considered. Using the Koyck scheme, it has been rewritten like this. Now the question is, can we estimate this model using ordinary least squares? The answer is no. There are two reasons why we cannot estimate this model. One is we have to estimate an infinite number of parameters. We have to estimate an infinite number of parameters. That is one problem. The second one is, it violates a very important assumption of the classical regression model, namely that linear in parameters. Beta 0 lambda square, then beta 0 lambda cube, etc. So it is not a linear in parameters model, it is non-linear in parameters model. So we cannot estimate this model. Now Koyck suggests a very ingenious solution to this problem. Let us see what is the method suggested by Koyck. Koyck lacks this one time period. So yt minus 1 is equal to alpha plus beta 0 x t minus 1 plus beta 0 lambda x t minus 2 plus beta 0 lambda square x t minus 3 plus etc. ut minus 1. Lag this one time period, yt minus 1. Then we multiply this with lambda. So lambda yt minus 1 is equal to alpha lambda plus beta 0 lambda xt minus 1 plus beta 0 lambda square xt minus 2 plus beta 0 lambda cube xt minus 3 plus etc. lambda ut minus 1. We multiply throughout with lambda. Then yt minus lambda yt minus 1, yt minus lambda yt minus 1 is equal to alpha into alpha into 1 minus lambda plus, there is a beta 0 xt here. This we have taken beta 0 xt plus, as you can see, beta 0 lambda xt minus 1 cancelled, beta 0 lambda square xt minus 2 cancelled, all these terms will be cancelled. So plus ut minus lambda ut minus 1, ut minus lambda ut minus 1. Subtracting, this can be written as yt is equal to alpha into 1 minus lambda plus beta 0 xt plus, this term is taken to the right, lambda yt minus 1 plus ut minus lambda ut minus 1. Remember this equation. This transformation is known as Koyck transformation. This transformation is known as Koyck transformation. We started with an infinite distributed lag model. By using the mechanism generating the model, we rewrite it like this: lag it one time period, multiply it with lambda, subtract this equation from this, and making some rearrangements. Yt is equal to a function of xt and yt minus 1. Now we have to estimate only 3 parameters. These parameters are alpha, beta 0 and lambda. We have to estimate only 3 parameters: alpha, beta 0, lambda. Now this is known as Koyck transformation. Koyck transformation. And if you compare this with this, you will see that alpha, this beta 0 xt is here, intercept is there, then beta xt minus 1, xt minus 2, etc. are replaced by yt minus 1. Yt minus 1. Now let us see what are the features of Koyck transformation. One feature of the Koyck transformation is we started with a distributed lag model and ended up with an autoregressive model. Ended up with a autoregressive model, as we have considered initially. So it means that any distributed lag model can be converted into autoregressive, and the autoregressive model can be converted into distributed lag, so that we can specify dynamic nature of relationship either by autoregressive model or by distributed lag model, or a combination of both autoregressive distributed lag model. The second feature is, in this Koyck transformation, yt minus 1 is an explanatory variable. Yt minus 1 is an explanatory variable. In the classical linear regression model, it is assumed that xt is non-stochastic. Even if it is stochastic, it is not correlated with the disturbance. Now let us write this as Vt. But yt minus 1 is there. Since yt is stochastic, yt minus 1 is also stochastic. So there is a possibility that yt minus 1 will be correlated with vt, and it creates estimation problems. So we have to analyze whether yt minus 1 is correlated with the error term vt or not. If correlated with vt, we cannot apply OLS to estimate the parameters, because the resulting estimators are not only biased, they are also inconsistent. As we will see later, yt minus 1 will be correlated with this vt. That is, the classical assumption will be violated. That means OLS cannot be applied to estimate the parameters of the Koyck model. What we use is the instrumental variable method. Now, a third feature is, in the original model, the error term is ut. In the new model, it is vt. Vt is equal to ut minus lambda ut minus 1. Now, if ut satisfies all the classical assumptions, vt will not satisfy all the classical assumptions. As we will see later, if ut satisfies all the classical assumptions, vt will be autocorrelated. So we will face the problem of autocorrelation in such models. Autocorrelation in such models. Also, remember this, as this is an autoregressive model or using time series data, we cannot test autocorrelation in this model by Darwin-Watson D. Darwin-Watson D. The reason is that it violates an assumption of the use of Darwin-Watson D. To use the Darwin-Watson D, an important assumption is that lagged value of the dependent variable must not be an independent variable. If you use Darwin-Watson D to detect autocorrelation, in most cases you will get the value of D as equal to 2 or close to 2. Means there is no autocorrelation. So you will get the wrong result that there is no autocorrelation, when actually there is autocorrelation in the data. So remember, these are the features of Khoyak transformation. We start with this model, we cannot estimate it. So the transformation suggested by Koyck is this. We ended up with a distributed lag model, and these are the features. We cannot apply OLS to this model to estimate the parameters due to the problems mentioned. Anyway, also remember this. In the distributed lag models, beta 0 gives the impact, value of the impact multiplier. Beta 0 and beta 1, beta 0 plus beta 1 will give you the proportion of the impact felt in the second period. Beta 0 plus beta 1 plus beta 2 in the third period, etc. So the partial sums will give us the impact, the proportion of the impact felt in different time periods. But in practice, to understand better the properties of distributed lag models, the impact felt, the time required for obtaining the proportion of impact felt, we calculate two quantities, namely the mean lag and the median lag, to describe the structure of relationship in the distributed lag model. So our next concern is the calculation of mean lag and median lag in the Koyck model, and we generalize it. So this is the Koyck model, and this is a very important model, and study this properly. This is the equation to begin with. This is the equation we end up with, and calculating the values of impact interim multipliers, etc. We can calculate the proportion of the impact felt in any time period. But in practice, to get a better understanding of the nature of lag structure, we calculate mean lag and median lag. and the calculation of the mean log and median log is our next concept.